Today we want to continue looking at exponential functions and percent change. We know that exponential functions are used to describe a pattern of repeated multiplication, and we also see that increasing or decreasing by some percent means that we will be multiplying. So exponential functions can also be described with percent change, with a percent increase or a percent decrease, where we're multiplying by more than one or multiplying by something less than one, but still more than zero. So let's take a description. Y is equal to 28 when x equals 0. And let's describe the function with percent change. And let's say that y is increasing by 12%. And let's say that this happens every 6 units. We have the same things that we always have when we're describing an exponential function or a function with a pattern of repeated addition or multiplication. We have a starting point, what's happening to the y, and then how often that happens. What we want to be able to do is look at the description increasing by 12% and turn that into some way to something to multiply. So we want to be able to translate this part of the description where we say y is increasing by 12% and say that this is equivalent to saying that y is multiplied by 1.12. Everything else stays the same. Y is still 28 when x is 0. We're just changing how we're describing things. Y is multiplied by 1.12 every 6 units. Once we have the multiplying parts, we can write an equation for what's going on. We could say that y is equal to, we'll start with 28, and then we'll multiply by 1.12. And we're doing this a bunch of times, so we'll use an exponent. We'll raise this to an x. But we only multiply by 1.12 every time we get a multiple of 6. So to make the step size equal to 6, I raise this to the x over 6 power. So by translating our increasing by a percent into a multiplier, we can write the equation describing what's going on in the function. If we want to build a table of values, we want some sample values for what's going on in this function. We know that we'll start at 0 and 28. And from 28, after 6 units, we will increase by 12%. So one way we could describe this is to say we'll increase by 12%. But for something to increase by 12% is to multiply by 1.12. 1, because we have to pay for the item as well as the tax, and the 0.12, that's the tax. So I could take the 28 and multiply by 1.12. This gives us the same thing as if we start with 28 and add 12% of 28, 31.36. The next step would be at 12, where we could add another 12%, which is the same as multiplying by 1.12. So if I take my 31.36 and multiply by 1.12, we'll be at 35.1232. We'll call it 35.12. This is the same thing that we would get if we took 31.36 and added 12% of 31.36. So adding a percent is the same as multiplying. We also want to be able to do the same thing with a decreasing function. So in this case, y was increasing by 12%, so our multiplier was 1.12, because we take 1 plus a 12%. If we just take the 12% and add that to 100, that gives us 112%, and we can turn that into a decimal. So the easiest way to think about this is to say 100% increased by 12% is 112%. Then as a decimal, that's 1.12. So start with 100% of a thing, and then increase by 12% of a thing, and you'll have 112%. It's useful to think of it in full terms of percent, because then we don't have to worry about decimals, because we don't like decimals. So just move it over 2 places, and you won't have to worry about it anymore. So let's suppose that we want y to start off at 36 when x equals 0. And let's suppose that y is decreasing by 24% every 6 units. Same format that we had describing, same format that we've used for describing linear or exponential functions before. Where to start, what's the change, how often do we make that change? In this case, since y is decreasing by 24%, we can turn this into y is multiplied by, we'll subtract 24 from 100, so we'll take 100 minus 24, and that's going to be 76. So multiplied by 0.76 every 6 units. Because we think about if we're losing 24%, then we're keeping 76%. That's where the subtraction comes in, because we know that increasing should mean plus and decreasing should mean minus. And we want to turn that into multiplication. Remember, the big idea is that 1 is in the middle of multiplication. So 1 plus the rate will give us an increasing, and 1 minus the rate will give us a decreasing. But now that we have the multiplier, we can write an equation. Y is equal to 36. And then we're multiplying by 0.76. And since we're doing a bunch of multiplication, we'll use an exponent. And since the step size is 6, we'll raise to the x over 6. And now we have an exponential equation for what's going on in this sentence. If we wanted to make a table of values like we usually do, these are the 3 different kinds of description that we're working with right now. If we take the 36 and subtract 24%, that should be the same as multiplying by 0.76. So I'll take 36 times 0.76, and that'll give us 27.36. We only subtract that much after 6%. We can also think about this as a subtraction problem. If I take the 36 and subtract 24% of 36, be at 27.36. If I take the 27.36 and multiply by 0.76, that'll put us at 20.79 after 12 units. We can also take the 27.36 and subtract 24% of 27.36, and we'll be at the same thing. Multiplying by 0.76 is the same as subtracting 24%. The equation is important because we might want some weirdo values. Of course, Multiplying by 0.76 is not something that we do so often that these aren't just weirdo values. But we can also determine what's happening every 1 unit. So as an extra question, we might want to think about what's happening every 1 unit. So if y equals, so let's just take this one as an example. If y is equal to 36 times 0.76 to the x over 6, we know to read this as y is decreasing by 24% every 6 units. So the 0.76 indicates that y is decreasing by 24% every 6 units. But this raises a question. This is what's happening every 6 units. What's happening every 1 unit? What if we wanted to write the equation in the way we write a linear equation, y equals mx plus b? To write the slope m, we take the rise and just divide it by the run. It's that simple. But it's different for exponential functions. Oops. Let's just take two values, x and y. We know that when x is 0, y is 36. One way to find out what's going on every 1 unit is to just figure out what's going on after 1 unit. If I take 36 and multiply by 0.76 to the 1 over 6, after 1 unit, we'll be at 34.39. And if we want to figure out what did we multiplied by, we just take the 34.39 and divide by the 36, and that'll tell us how we multiply 36 into a 34.39. So if I just take this number and divide it by the 36, I get 0.955. So this comes from taking the 34.39, where we ended up, and dividing it by the 36, where we started, to arrive at the 0.955. If we look at what's going on at 2 units, so if I take 36 and multiply by 0.76 to the 2 over 6, we'll be at 32.85. So at 2 units, we'll be at 32.85. If I want to figure out what the multiplier is here, if I take the 32.85 and divide by the 34.39, that should give us the same multiplier of 0.955. If I take the 32.85 and divide by the 34.39, that gives us the 0.955. Notice it's a little bit different, very little bit different than the 0.955 we had before. In the 0.955 we had before, stuff hadn't been rounded off. So if I take the 32, if I use more decimals, 32.85289.897, and divide that by the 34.39 with more decimals, 34.39046.907, then I do get the same 0.955 we had before. Let's suppose we want a little bit more efficient way. Suppose that we happen to be into formulas because we've been poisoned by previous math classes to think that formulas are great things. I don't need to understand what's going on as long as I have a formula. Let's think about where this 34.39 came from. 34.39 came from taking 36 and times the 0.76 to the 1/6 and dividing it by the 36. If instead of just grabbing the calculator right away and making these calculations, I can see that the 36 doesn't make a difference in this 0.955. That makes sense. The 0.955 is how things are changing, not where they started. Because it's a pattern of repeated multiplication. It doesn't matter where we start with y. After 1 unit, we'll be multiplying by 0.955. So it makes sense that the 36s will cancel out, and we can calculate this as 0.76 to the 1/6, which is 0.955. If I look at the other way, I got this 0.955, and instead of just calculating the numbers, if I write out what my calculation consists of, I'll take 36 times 0.76 to the 2/6 and divide by 36 times 0.76 to the 1/6. Once again, just like in the previous calculation, the 36s didn't matter. In this calculation, the 36s don't matter either. That makes sense. The 36s are where things start, and we're asking questions about how things are changing. So we have 0.76 to the 2/6 divide by 0.76 to the 1/6. And we know that if we're dividing something like x to the 5th over x to the 3rd, I can subtract the exponents. So we'll do the same thing here. 2/6 minus 1/6 is 1/6. And it works out to the same 0.955 that we had before. So that's how we can simplify our description. If y is decreasing by 24% every 6 units, we can simplify that to multiply by 0.955. And now we can see how it's changing every 1 unit. So if we have a description that says y is multiplied by 0.955 every 1 unit, a description involving multiplication, I can turn this multiplication description into percent change. I can turn this into y is decreasing by, let's see, I have 95.5, so I'll take 100 and subtract the 95.5, decreasing by 4.5% every 1 unit. It's slightly different than taking 24 and dividing it by 6. 24% every 6 units is not going to be 4% every 1 unit. It's going to be 4.5% every 1 unit. So the interesting question is, why can't we just take the 24% and divide it by 6? That is the important question for me to not answer. That's the important question for y'all to think about. Why is it not just 24? Why is it not just 24% every 6 units should be 4% every 1 unit? Why can we not just split things up by dividing by 6 units? All right, that's all I wanted to talk about today. So that'll do it for today. That'll do it for this week. Everybody have a nice weekend, and I will see y'all on Monday. Thanks for playing.